Episode 3. The moon is born. On a clear night, step outside and look up. The moon, that pale disk, cratered and familiar, has watched over Earth for 4.5 billion years. It has witnessed the entire history of life on our planet. It has seen the first cells divide in the ancient seas. It has watched as animals crawled from ocean to land. It has lit the nights for dinosaurs and for the first humans. It has inspired poets and lovers, guided sailors and travelers, marked the passage of time for every civilization that has ever existed. The moon is so much a part of our existence that we take it for granted. But the Earth, having a moon, especially a moon as large as ours, relative to the size of the planet, is unusual. Mercury and Venus have no moons at all. Mars has two tiny captured asteroids, barely worth the name. The gas giants have many moons, but they're all small compared to their massive parent planets. The Earth's moon is different. It's enormous, 1/4 of the diameter of Earth itself. If Earth were the size of a basketball, the moon will be the size of a tennis ball, far larger in proportion than the moons of other planets except Pluto, which is not really a planet at all. The size is significant. The moon is not some minor accessory to Earth. It's a parent, a companion, a massive, enough to influence our planet in profound ways. But where did the moon come from? How did Earth acquire such an unusual satellite? For centuries, this question puzzled scientists. Early theories proposed that the moon formed alongside Earth from the same cloud of material, or that it formed elsewhere in the solar system and it was later captured by Earth's gravity, or even that it was somehow flung off from Earth's surface by a rapid rotation. None of these theories worked. They all had fatal flaws, problems with physics and chemistry or dynamics that made them impossible. The answer, when it finally came, was far more dramatic than anyone had imagined. The moon was born in violence, in the greatest collision Earth has ever experienced, an impact so tremendous that it nearly destroyed our planet and fundamentally shaped its evolution for billions of years to come. This is the story of that collision, of the birth of the moon, and of how Earth and its new companion settled into the partnership that continues to this day. We must return to the late Heian, perhaps 4.5 billion years ago, some tens of millions of years after Earth's initial formation. The solar system was still young, chaotic, still filled with planetary embryos and large planetesimals final destinations. The inner solar system had four main survivors of the planet building process: Mercury, Venus, Earth, and Mars. But there were others, smaller bodies, protoplanets that had grown to significant size but had not yet collided with the main planets. One of those bodies orbiting the Sun in a path that sometimes brought it near Earth's orbit has been given a name by scientists: Theia, after the Greek Titan who was mother of Selene, the moon goddess. We do not know much about Theia, and because it no longer exists, but we can infer some things from computer models and from the chemistry of moon rocks. Theia was probably about the size of Mars, roughly half the diameter of Earth, with perhaps 10% of Earth's mass. It had differentiated, like Earth, into an iron core surrounded by a rocky mantle. It had formed from the same general region of the solar nebula as Earth, so its chemical composition was similar, though not identical, to our planet's. For millions of years, Theia followed its orbit around the Sun, and Earth followed its own orbit, and the two didn't meet. But orbits in the young solar system were not stable. Gravitational interactions with other planets, especially with the massive Jupiter, constantly perturbed the orbits of smaller bodies, changing their paths in small incremental ways. Over time, these small changes accumulated. The Theia's orbit and the Earth's orbit began to intersect. The collision, when it came, it was not head-on. If Theia had struck Earth directly, traveling in opposite directions, the both planets would be likely to have been completely destroyed, shattered into fragments that might or might not have reaccreted into new planets. But the impact was oblique, a glancing blow, with Theia striking Earth at an angle. This made all the difference. Computer simulations of the impact run on powerful supercomputers using our best understanding of physics and planetary science can give us a picture of what happened. The details vary depending on the exact angle and speed of impact, but the overall story is consistent. Theia approached Earth at a velocity of perhaps 10 miles per second, roughly 40,000 miles per hour, moving at an angle of 45 degrees to Earth's surface. As the two bodies drew near, their gravitational fields began to interact. Earth, being larger, pulled more strongly on Theia, accelerating it inward. Theia, in turn, pulled on Earth, distorting both planets, raising tidal bulges thousands of miles high. And then they touched. The initial contact was between the outer layers and Earth's outer layers, rock meeting rock at hypersonic speeds. The kinetic energy of the collision was instantly converted to heat, and the temperature at the point of impact reached tens of thousands of degrees, hot enough to vaporize rock instantly. A shockwave propagated through both bodies, traveling at miles per second, compressing and heating the material it passed through. Within seconds, the entire surfaces of the both planets had been vaporized or melted. Within minutes, the cores of both planets were in contact. Thea's iron core, perhaps thousands of miles in diameter, plunged into Earth's mantle like a bullet into water, creating a cavity and sending shockwaves reverberating through the planet. The force of impact caused Thea to disintegrate, its core, along with a significant portion of Earth's mantle that had been liquefied or vaporized by the impact, was blasted into space. A plume of vaporized rock, iron droplets, and molten debris erupted from the impact site, a fountain of destruction that rose thousands of miles above the Earth's surface. Most of the mantle material and some of the Earth's material was blown into the orbit around the Earth. Some escaped Earth's gravity entirely and was lost to space. Some fell back to Earth in a rain of molten rock that lasted for days or weeks. But a significant amount, perhaps a moon's worth of material, remained in orbit, forming a ring of debris around the battered planet. Meanwhile, Thea's iron core, having plunged deep into the Earth's interior, did not escape. It sank through the mantle, merging with the Earth's core, increasing Earth's total mass and adding to the planet's iron content. This is one of the reasons Earth has such a large core for a rocky planet. We incorporated the core of another world. The energy released by this impact was beyond comprehension. It was equivalent of billions of nuclear weapons detonating simultaneously. The entire planet was partially melted. The crust, such as it was obliterated. The atmosphere was blasted away into space, at least heavily eroded, for a brief moment, measured in hours or days. The Earth may have been surrounded by a glowing envelope of vaporized rock, a cloud that was so hot it radiated light like a star. If there had been any life on Earth before this impact, and there almost certainly was not, it would have been completely sterilized. Nothing could have survived. The entire planet was returned to a molten state, back to the conditions of the early Hadean, perhaps even worse. But from this destruction, something new was being created. The ring of debris orbiting Earth, the remains of Thea's mantle, and the fragments of the Earth's mantle began to evolve. The material was a mixture of molten rock, solid chunks, and vaporized silicates, all orbiting Earth in a chaotic turbulent disk. This ring may have stretched from a few thousand miles above Earth to perhaps 50,000 miles out, a vast destruction surrounding the planet. Gravity and collisions began to organize this chaos. Particles in the ring collided with one another. Some collisions were destructive, shattering both objects, but others were gentle enough that the objects stuck together, held by their mutual gravity. Bit by bit, the debris began to clump together, forming larger and larger aggregations. This process, the same process of accretion that had formed the planets themselves, proceeded rapidly. The ring was dense with material, and collisions were frequent. Within a remarkably short time, perhaps just a few years of decades, most of the debris had collected into a single large body. The moon had formed. The young moon was so close to Earth, much closer than it is today. Perhaps maybe 50,000 miles, 15,000 miles compared to the current average distance of 240,000 miles. At this distance, it would have appeared enormous in the sky, perhaps 15 times larger than the moon we see today, a vast glowing disk that dominated the heavens. And it was glowing. The moon, like Earth, was molten from the energy of its formation. Its surface was a magma ocean similar to the magma ocean that had covered Earth in the early Heian. The moon was essentially a ball of liquid rock, heated by the countless collisions that had built and heated by the countless collisions that had built it, and by the tidal forces from the nearby Earth. The tides raised by Earth on this close, molten moon were tremendous. Earth's gravity pulled it on the near side of the moon much more strongly than on the far side, stretching the moon into elongated shape. As the moon rotated, these tidal balls moved around the moon, and the friction from this movement generated heat, keeping the moon molten. Over time, the moon began to cool and solidify just as Earth had. The surface cooled first, forming a crust of anorthosite, a light-colored rock rich in calcium and aluminum. This is why the lunar highlands, the bright areas visible from Earth, are so pale. They are made of this ancient crust formed when the moon's magma ocean solidified. As the moon solidified, it also moved away from Earth. The tidal forces between Earth and the moon transferred angular momentum from Earth's rotation to the moon's orbit, causing the moon to gradually spiral outwards. This process continues to this day. The moon is currently moving away from the Earth at a rate of 1.5 inches per year, a slow drift that will continue for billions of years. This early close moon had profound effects on Earth. The tidal forces it exerted on the molten or partially molten Earth were enormous, far greater than the tides we experience today. These tides may have helped drive the convection of Earth's mantle, mixing the interior and speeding the cooling process. They also affected Earth's rotation. Before the impact, Earth probably rotated much faster than it does today. A day may have been only 5 or 6 hours long. But the collision with the tidal interactions with the newly formed moon slowed Earth's rotation. The tidal bulge raised on the Earth by the moon's gravity acted as a brake, dissipating rotational energy through friction. Over millions of years, the Earth's rotation slowed and the length of the day increased. Eventually, the day length stabilized at 24 hours, though it continues to lengthen very slowly even now. The moon's gravity not only gave us the tides and lengthened our day, but it also stabilized the Earth's axial tilt, the angle at which Earth's axis is tilted relative to its orbit around the Sun. Without the moon, Earth's axial tilt would be unstable, changing chaotically over time due to gravitational perturbations from other planets, especially Jupiter. These changes could be dramatic, swinging from nearly 0 degrees to 80 degrees or more. Such changes would cause wild swings in climate, making the poles tropical at some times and the equator freezing at others, creating conditions that would make the evolution of complex life difficult or impossible. But the moon's gravity acts as a stabilizer, keeping Earth's tilt locked at about 23.5 degrees, varying by only a degree or two over millions of years. And this stability has given Earth a stable climate, at least in the sense of having consistent seasons and predictable patterns for billions of years. It is one of the moon's greatest gifts to life on Earth, though it is invisible and often underappreciated. The moon also plays a role in Earth's tides. Of course, the rhythmic rise and fall of the ocean that occurs twice a day. In the deep past, when the moon was closer, these tides would have been far more dramatic, perhaps hundreds of feet high, crashing onto the shores of the primitive continents. Even today, tides are significant. They mix the ocean's circulating nutrients. They create intertidal zones, regions that are alternately covered and uncovered by water, which may have been crucial environments for the transition of life from sea to land. And the moon provides light at night, reflected sunlight that has illuminated Earth's nights for billions of years. Before artificial light, this was the only light available after sunset, and it shaped the behavior of countless species, from nocturnal hunters to migrating birds to sea turtles that used the moon to navigate. But let us return to the immediate aftermath of the impact, to the days and the months and the years following the collision with the Earth was a wreck. The impact had melted much of the mantle and completely destroyed any crust that had existed. The atmosphere had been stripped away, or at least heavily eroded. The surface was once again a magma ocean, a glowing red hot, convecting and churning. And in the sky, the newly formed moon hung enormous and bright, itself a ball of molten rock, tightly locked to Earth, so that the same face always pointed towards the Earth, just as as it is today. Two bodies, Earth and Moon, were linked by gravity and by their shared history. They, they had been forged together in the same catastrophic event. Material from Theia had been incorporated into both. They were, in a sense, siblings, children of the same collision. Over the following millions of years, both Earth and the Moon cooled and stabilized. The Moon, being smaller, cooled faster. Its magma ocean solidified, forming the crust that we can still today, see today in the lunar highlands. Volcanic activity on the Moon created the dark maria, the lunar seas, the vast plains of the basaltic lava that erupted from the Moon's interior and flooded the low-lying basins. But the Moon's geological activity did not last long. Within a billion years or so, the Moon had cooled enough that its interior solidified. Volcanic activity ceased. Plate tectonics, if they ever existed on the Moon, stopped. The Moon became geologically dead, a frozen snapshot of its early history. Earth, being larger and with more internal heat, remained geologically active. The magma ocean solidified, forming a new crust. The atmosphere began to rebuild itself through volcanic outgassing, and eventually, as we will see today in the next episode, water began to accumulate on the surface, once more forming the first oceans. The impact with Theia was the last of the great collisions of Earth's formation. After this, the inner solar system was largely cleared of planet-sized objects. There would still be impacts, many of them from asteroids and comets, and we will discuss those in the future episodes, but nothing on the scale of the impact would ever strike Earth again. In a sense, the impact marked the end of Earth's childhood and the beginning of its adolescence. The planet was fully formed, at least in terms of mass. The Moon was in place. The stage was set for the next great chapter of Earth's history, the formation of the oceans and the emergence of life. But before we move to that chapter, let us consider what we have learned about the Moon and its importance. The Moon is not just a pretty object in the night sky. It's the fundamental part of Earth's system, influencing our planet in ways both obvious and subtle. It gives us tides, it stabilizes our axial tilt and providing climate stability. It slows our rotation, giving us a reasonable day length. It may have played a role in the origin of life by creating tidal pools and mixing the oceans. It provides light at night, which has shaped evolution and ecology, and it is record of Earth's early history. The Moon's surface, untouched by plate tectonics or erosion, preserves craters from impacts that occurred billions of years ago. By studying the Moon, we'll learn about the bombardment history of the inner solar system, about the composition of Earth's interior, about the conditions in the solar system. The Apollo missions, which brought back hundreds of pounds of lunar rock between 1969 and 1972, revolutionized our understanding of the moon and of Earth. Analysis of these rocks revealed that the moon's composition is similar to Earth's mantle, but lacks the iron-rich core that Earth has. This was a crucial clue that led to the giant impact hypothesis, that the theory that the moon formed from debris blasted into orbit by collision with the Mars-sized object. Before Apollo, the origin of the moon. Before Apollo, the origin of the moon was a mystery. Now we understand it, or at least in broad outline. The moon is a child of a catastrophe, born from the greatest impact in Earth's history, forged in fire and violence, and cooled into the serene companion we see today. It is humbling to think that this beautiful, peaceful object, this gentle light in the night sky, has such a violent origin, but it is also inspiring. It reminds us that even from destruction, creation can emerge. Even from chaos, order can arise. The universe is not gentle, but it's generative. It builds even as it destroys. As we close this episode, take a moment, if you can, to step outside and look at the moon. See, it's not just a familiar sight, but as a witness. See it not just as a familiar sight, but as a witness to the Earth's entire history. See it as a sibling world, born from the same cosmic collision that gave Earth its final form. See it as a stabilizer, a protector, a partner in the long dance of gravity and time. The moon has been with us from nearly the beginning, and it will be with us, slowly drifting away for billions of years to come. It's a reminder of where we came from, of the violence and the beauty of the universe, of the deep connections between all of the objects in the solar system. In the next episode, we will see Earth begin to cool again after the Dia impact. We will watch as the atmosphere rebuilds itself, and we will witness one of the most important moments in our planet's history. The first rains, the gathering of water, and the formation of the oceans. From fire and rock, a blue planet will emerge. The stage will be set for life. But for now, we pause here at the end of the age of giant impacts, with Earth and the moon newly formed, both glowing with the heat of their violent birth, both beginning the long, slow journey